Hello. Okay, it looks like it's all set. All right, so all right, it is recording. Hopefully, nothing goes wrong with this one. Yeah. So, all right. So I could talk about whatever. I could just start about my torque if you want. I've just read the homework problems, so I suppose. So we could talk about them, or I could just start talking about torque in general.
Maybe torque in general, and then the first one is that.
Sure. So
they're all.
Yeah, the first one. Okay, so the first one is it's within the book. I suppose it's. Oh, it's because you just have to pick one, I think. Okay, that's kind of interesting. Anyway, and then the second question, they ask you to do like 3.5, like the problem 3.5, not the.
Yeah.
Right? And that, they say somewhere, it references example 3.3.
Yeah.
Which is actually a good example. So I'm actually going to start with that. So this is actually example 3.3, but it's just a good example in general. So it's kind of the simplest example of linear motion to rotational motion. Yeah. So that's a good one. So I'm not gonna do literally the exact like the numbers they do because that's not really as interesting. Okay, so let's say you have a pulley or an Atwood. Someone's called an Atwood machine.
Yeah.
I don't know who Atwood is, probably someone from a long time ago, but somehow it just means a pulley. And, well, it usually means there's an extra condition, which is that if it has a rope on it, the rope does not slip. That's very important. Okay, so what that means is that if you have, like, let's say you have a pulley and you have a block here and a block on both sides, right? When you think of this, if you want to imagine this block falling and this one going up, it has to rotate the wheel too. Now I believe they'll probably say that everything's massless here, like the wheel is massless, which is fine. Let's see what they actually say. They don't say anything about it, which is sort of strange. Oh, wait. Oh, no. Okay, they do say it. Yeah, so it does have mass. Okay. Well, anyway, so yeah, so what I said is important. It's important to know that if the blocks move, the wheel has to turn. Okay, it's not like a thing where the thing can slide back and forth. That would be a different kind of problem, I guess. But anyway, let's do the first example where we don't have this. We just have one weight, and let's say it has a mass m. And now, let's just see, I guess, what happens. I guess we need something to solve for. Let's say after this falls a height h, okay, then, I don't know, what is the angular velocity of the wheel? So this is omega, right? This is the angular velocity. Or, I mean, they could also say angular momentum. So angular momentum would, in this case, would just be I times the angular velocity, right? Because it's just like momentum is mass times velocity kind of thing. So anyway, they could ask for these. They don't usually ask for angular momentum in really anything. Like, that's not a very common thing to solve for because it's just like with regular momentum, linear momentum. I shouldn't call it regular, I should call it linear momentum. Like, you should know what it is and the definition and how to write it, but like they don't really ask you to solve for it because it's sort of not an interesting variable by itself. Like conservation momentum is really important, but like writing in the the units of momentum aren't even a good unit. It's like kilogram meter per second, which is kind of a weird unit. So anyway, so angular momentum is like an important quantity, but it's not necessarily important that you were not going to solve for it very often. We're just going to use it a lot. But anyway, so what we could do is, well, how would we do this? Well, one way is just with energy, right? Because you can imagine, well, there's two objects. This one has some, so at the beginning of the system, let's just set up an energy thing and see what it looks like. So at the beginning of the system, where is all the energy? Well, the only thing here, assuming this is not moving at the beginning, the only thing that's happening is that this has some potential energy, right? It's going to fall. So we could write the initial energy is just this, right? And now what's the final energy? Well, this has no more height, so there's no potential energy. But what is happening? So there's some kinetic energy in this, right? Because it's falling. So that is going to be 1/2 m v squared. So it's after some height h, it's going to be falling at speed v. Okay, so I'm just going to make up a v. I don't want to leave this in the answer, obviously, because, well, we'll see. But I don't want to make up a, like, m we're given and h we're given, but we're not given v. So, and we're given r. And now what else, though? There's some other kinetic energy, right? It's the rotational kinetic energy. So we have to, of course, include that. And so what's the rotational kinetic energy? It's looks basically just like the linear kinetic energy, but it's just going to be 1/2 I omega squared, right? But he definitely mentioned this yesterday, right? So
I remember.
KE rotation is this thing. This is KE linear. So for things that are spinning, of course, it's so another way you can think of it is, well, no, that's a, I don't think it's anything, but yeah. Yeah, and there's two objects and we have both of them covered. The only thing I was going to say is that we don't want to count things twice. Like, you don't want to count things twice for energy, but like there's sort of no way to confuse them because, like, if you thought this had rotational energy, you'd be like, well, what's omega and I? Like, it doesn't make any sense. So you kind of already count everything. But the important part is that we have two objects with energy at the end, and we have two terms here.
If there were like two for the, how would this equation be set up?
If there were two,
Like if there's one on either side.
Oh.
Like do you do them individually?
oh, we'll see.
Okay.
Yeah, don't worry. We'll
Okay.
see. So actually, with those problems, it's usually better to do them kinematically.
Okay.
So, and I will do this exact problem kinematically too, to show you how to do that, because that's the more likely problem with torques and stuff.
Okay.
There's no torques here because we're doing energy, but I just want to show you because this is important. This is actually a little easier than the kinematics way, because we sort of already know about energy, right? It's just a new type of term here. And now we have to know that because it's a disk and they told us the mass, I'll say the disk has mass, I guess I'll just say m disk. I should have used capital M for this and little m for this, but whatever. So it has mass, they told us that in the problem, so we could use that. Now we have to know what I is for the disk, right? When the disk is rotating, well, we want to solve for omega, so we can leave that in our answer. So what's I of the disk? Well, we have to kind of look it up, and it's like 1/2 mr squared, is that right? I think that's right. M disk r squared. So I'll just write those over here. For a, yeah, I believe it is. For a disk, I is 1/2 mr squared, right? M is the mass of the whole disk, of course, r is the radius. For a hoop, it's mr squared, okay? A hoop is and now, this seems like it's sort of more in some sense than this, which is a little bit weird because you think, well, a hoop seems like less material, but it's function of the mass. So a hoop would probably weigh a lot less. But if you had a disk and a hoop with the exact same mass, the hoop's gonna be really heavy. I mean, they weight, but like they're gonna be really dense, kind of thing. So you can imagine it's actually hard. So another way to think of this moment of inertia is how hard it is to spin something. So when something has, now of course, if something's heavier, it will be harder to spin, of course. So that's what the m is for, right? So if you double m, you have more inertia, more rotational inertia. It's harder to spin. If you put all of that mass like in a disk, where now some of the mass is near the middle, right? So if I make this shape. Well, anyway, if I have a disk and I want to spin it, all I need to do to spin it is the outside needs to go pretty fast, but the inside only needs to go not that fast. So it's actually not that hard to spin a disk. It's a little, I don't know, it's very imprecise what I'm saying, but it's not that hard to spin a disk because you don't actually need to get all of the mass going at really fast speed. With a hoop, if you had that same amount of mass, you would need to get all of it to go really fast. So that's why it's actually, in some sense, twice as hard. Now, you can't figure out, well, I can't figure out, at least in my head, why it's twice as hard for, like, you have to do that integral that he was talking about with it's the integral of dm of r squared, where r is a function of the mass. Now, this is complicated and sort of unintuitive. So you don't actually do this, because he's solved, well, he didn't do it.
Was he just using that for like conceptual purposes? Like,
The integral?
Like proof, like for a proof.
Yeah,
Or we
because
don't have to use that.
yeah, I doubt you'll ever have to use the actual integral.
Okay.
You will probably have to use the parallel axis theorem. actually, let's do that real quick. So I'm sorry, I'm taking a break from this,
So
but like,
he stressed that, yeah.
yeah, the parallaxis theorem is very important because, and now let's actually use it for a rod. And so this is probably on, he gave you like a sheet, right? With the,
Yeah.
oh, okay. Oh, perfect. These are the two I was going to look at. So actually, let's talk about, so there's two rods. There's one that's rotated around the center. Okay, and when I say rod, I mean it's rotated like this. Okay, it's not rotated through the, like, it's not rotated like a,
Yeah.
yeah, because if it was, note that this disc, so a disc looks like this, right? And it's rotated like that. A disc, there's no term in here that talks about the thickness of the disc.
Yeah.
And it's actually because it's, and what that means is that it's independent of the thickness. So if you made a disc that was like this, with a thickness D, right, or T, well, with D, let's say, versus with a lot thicker, D plus D prime, which is bigger, it doesn't matter. The I should be the same. I mean, of course, the mass might be different, but as long as if they have the same mass, it should be just as easy to accelerate. And this is called, there's some name, I forgot the name, but I don't think it's called the perpendicular axis theorem. That's actually a different thing. But there's another rule. There's like 3 rules with these. There's the parallaxis theorem, something called the perpendicular axis theorem, which you probably won't need to use. And there's a third thing which says that to extend something in the dimension that you're rotating it around doesn't affect the moment of inertia. So it'll always be true where if you take like, I guess this is kind of the only example, that if you take like a thin disc and make it into a cylinder with the same radius, the moment of inertia should still have the same form. It should still actually be the same values, assuming you didn't change the mass. Now, of course, if you stack things and try to rotate them, you're actually changing the mass in that case. But assuming you have like the same mass things that are different thicknesses, as long as the thickness is in the dimension that you're rotating it, they shouldn't affect it.
Cross-section never changed.
The cross-section never changed, exactly, because you can see that because in the integral, this is the integral, r is the distance from the center.
Right.
It doesn't say anything about and the distance just means like the distance from here to whatever the point is. Nowhere do they say vertical. There's no vertical reference here. There's a two, well, yeah. So this is actually, dm would be converted to like a 3-dimensional integral because it's a volume, so it's 3 dimensions. But nowhere in here do you actually care about the sort of the z component. You only care about the radial components. So this, yeah, in some sense, this is like the cross section. Like this is only dependent on the cross section. Anyway, so that's okay. So that was I'm going to try to limit the tangents because I'm already on a tangent from this problem. But I did want to show you this because this is really important. So this rod is rotated around the middle. Let's say it has a length L, and from the from the thing, we can see that it's ml squared over 12. Okay. Okay, and now let's see what if you wanted to rotate this rod, but you want to rotate it around the edge, right? So in other words, you want it to like this, right? You want the edge to be the axis of rotation, basically. So it's going like this now. It has the same length. Okay. Now, yeah. So here's what we could do. Well, we could just say, I know that if assuming this is uniformly distributed, they're all uniform masses. Like it's not like they have a dense part or a not dense part. What the parallaxis theorem says is that this I, I'll say end, is equal to I center, where this means the center of mass, where I meaning the axis of rotation around the center of mass, plus n d squared, where d is the distance to where we want to rotate it. So distance to axis from center of mass, right? So in other words, this is the separation between these two. Like this example, we have one axis. This example, we have another axis. The separation between their axes is d. Okay. So in this case, what's d? Well, we moved the axis a distance L over 2, right? Right, because remember this is all a function of the length, the whole length L. That's a little bit weird because we use the radius here, but in this case it's the whole length L. We moved L over 2, so d becomes L over 2. So I'm going to erase this actually. L over 2, L over 2 squared is L squared over 4, right? And now we have ml squared over 12 plus ml squared over 4, which is 4 ml squared over 12, which is ml squared over 3, right? It's the fraction thing, right? So I end should be ml squared over 3, right, by adding these. And actually, if we look, we see that he actually gave it to you, and it is indeed ml squared over 3. So this is a rod rotated around the end. We could also think of this as if you have two things at the same time. Let's say you stacked. Now this is a bit of a weird thing, but let's say you stacked. You have a cylinder, which is, remember, a disc. It's the same moment of inertia. And then you like stacked a rod on top of it, and you wanted to rotate them together. Then you would just add their moments of inertia together. Okay, does that make sense? Now, I'm not going to write it all out because you'll never see this in a problem. But the point is that if you have two things going like basically fixed together that have different moments of inertia, if you want to rotate them together, you just add their moments of inertia, okay? Now, we could use that for this problem by trying to find what is the moment of inertia of this. It's actually two rods with length L over 2 rotated around their ends. Does that make sense?
I get you. Okay.
So there's a rod with a length L over 2 over here and one over here. So what if we said it's I rod 1 plus I rod 2? That should be this, right? And now what is rod 1? Well, rod 1 is actually, it's this one, right? And so it's M, so it's ML squared over, sorry, I don't want to say, it's M something over 3, where L is now the length of the rod, but the rod, remember, it had length L over 2. So this is actually L squared over 4, right? What am I doing wrong? It looks like it's not going to work.
It's already L squared, so it's L.
Yeah, no, what am I, there's some, or 3, yeah. I mean, okay, what I'm supposed to be doing right now is saying this is the same exact thing, and they're both this over 12, but then we get double that. What am I? Oh, sorry, they have mass m over 2. That's what I'm doing. Okay. So each half rod here has mass m over 2, right? That's what I was forgetting. M over 2. The length is L over 2, so we square that and we get L squared over 4. And the moment of inertia has all that over 3, so we get that, right? And now because we have two of the rods and they're the same, I could just multiply by 2, right? That actually cancels that, and we get ml squared over the 4 and the 3 combined to give 12, and that's this. Right. So these theorems are actually true, in case you didn't believe them. So so I just showed that you could break any, so if they give you a complicated object that's rotating, often what they want you to do is there's basically two methods. One is the parallel axis theorem, which is like moving the axis to a parallel axis, obviously. And the other one is breaking things up or combining things by just adding their moments of inertia. But using those two things, you can pretty much, they'll never give you an object that you have to do an actual integral for. You can just use one of these methods. Or consider something like, extending I don't know what else they could extend. I mean, technically they could extend a sphere. Like if you have like a football shape that was technically, I don't know why they would tell you this, but technically it was like a sphere extended, then technically it would have the same ownership of a sphere. They're never going to ask you that, but it's really silly. But the point is that anything extended in the direction that you're in, the direction along this axis has the same moment of inertia. Anyway, all right, does that kind of make sense? Okay, hopefully it's still recording. Okay. All right, so now I'm gonna erase all this so we can actually do the problem. Well, actually, let's just do it over here now. I don't think it's gonna be that much more work because, okay, so here's the key thing. So now it looks like, well, we wanted to just solve for omega. What if we just rearrange everything and solve for omega? Now we are given m of the block, G is fine. H we're given. M is the same M. V we're not given. Okay, and then everything else here we're given. So actually we could solve everything, but we need to do something with the V. We can't just, like, it's not random what velocity it is, because it depends on, if it's a really heavy disk, it might be slower, right? So actually we have to talk about, and we want to solve for omega. So how can we relate V to omega? V is the linear velocity of the block at some point, and omega is the angular velocity of the wheel at the same time. That's very important. It's at the same time. Well, if the linear velocity is v, that means that it's pulling this string at velocity v. If a wheel is connected to a rope where it's being pulled at tangential velocity v, how do we write the angular velocity? We can just write that, right? R is the radius of the thing. So that's it. So as long as we plug in v equals r omega here, that's what we have to do. Plug in v equals r omega, because this v, basically what we have written in here is an equation with two separate variables, v and omega, and we actually know, because they're literally connected to each other with a rope, they can't be separate variables. They actually are the same variable. I mean, they're not the same variable, but they're the same. They're related by this r. So, which just means that the string, which goes around the outside, has tangential velocity r, meaning the wheel has tangential velocity r. Sorry, tangential velocity v, and so therefore the angular velocity it has is just v over r by definition of what angular velocity is. So that's very important, the fact that, like what I was saying, is it doesn't slip. Right? If it could slip, if this sort of rope could kind of slip off and maybe had some friction, it would be an incredibly complicated problem. But the fact that it doesn't slip means that this is true. So this, sometimes they call it the rolling without slipping. Without slipping. Because they'll usually say this exact phrase in these problems, and that literally just means that whatever the surface is, you can consider the tangential velocity to be like related to the angular velocity just by this. This is not, of course, true if it can slip, you could say, well, maybe the wheel doesn't move at all, and then of course it's not related at all. But anyway. Okay, so that's the energy way to do it. And then I'm not going to write it out, but you could just, now that we plug this in, everything except for omega is things that we're given, and we can just solve for everything. Okay, so now I'm going to erase everything, if that's all right. And we're going to do it the kinematics way, and then we'll add another block and see how that's actually not that much harder when we do that. Okay. So you can always use energy. So this is the start of there being multiple ways to solve problems. So I know they keep saying that, and it seems sort of obvious, that's true. But up until now, there's kind of been only one way to solve all the problems. I mean, there's one sort of obvious, the way they want you to do it, and they sort of try to make it hard to do it the other way. But in this case, in this exact case, there's literally two ways, and they're not, I don't even think one of them's easier. And so what we can do is say, I'll draw sort of the free body diagram. I'll just, and I'll say at this point, so yeah, let's draw a free body diagram. So this is what's happening. Here's some block of mass M. Yeah, that's fine. And this has M disk and R disk. So I'll just say R. Okay. And what's the free body diagram here? I'll draw a box around it so you know it's free body is not connected to anything right now. There's a force of gravity on it, mg, right? Oh, what's the force going up? The tension, exactly, yeah. So this has a tension T, okay? Now we don't need to say anything about it because, well, let's just wait for now. We don't need to say anything right now about it. It has some tension T, okay? Now, therefore, it's not gonna fall with acceleration G, right? Assuming the tension is not zero. Because you can see, if the tension was zero, it would fall with acceleration G. It would just be a free fall, I mean. But because there's some tension, it's not going to fall that quickly. So now let's see where on this picture, so let's draw, I'm going to just move this over. So we know this M disk and R, right? Right here, now what do we have the free body diagram of this disk? We have some tension here, right? Because tension has to, it's the same rod, the same rope or whatever, so it has to have the same tension pulling down. And now that's it. There's no other forces, right? I mean, every force that acts at the center, we don't have to worry about. Now, of course, there must be gravity, because if it weighs something, and there must be a thing holding it up. But because they're at the center, they're not actually going to have any torques on them, right? Torques at the center. So he made this point at the end of class that I don't think it was clear enough to really show you how important it is. Which is the fact that what he was saying, like, well, I'll get to it, but the point is that you can compute the torque. When you compute the torque, you have to compute the torque around a point. It's not like forces. Forces, you don't have to pick any points. You just say the force on the thing. But you can compute the torque around any point. Okay? So when you pick the torque, so in this case, we're picking the torque at the torque around the center. Okay? We're saying, at this point, what are all the torques on the object? Well, there's one force here, and we know that we could also write it as like R cross F, right? And we know that if this is R and this is F, the cross product must be non-zero because they're perpendicular. So there's some torque on it. Now, we picked the center because we don't care about the forces there. And of course, if we compute this again, the force of gravity, for example, how far is it from the center? 0. So this is 0. That's why the torque is 0 around the center. But we can compute the torque around any point, and it's totally fine. So that's the point he was trying to make. And I'll show you why this is really important when we do another problem. But okay, and so now we have, well, here we have the sum of the forces must be equal to ma, right? If we want to actually find the motion now, the motion is a. So this is what happens. So sorry, this is capital M, right? So the sum of the forces is ma, which means that the sum of the forces is what? Well, it's just T minus mg, right? So we have this. This is the equation for the block, right? And now what's the equation for the rotating thing? Well, we know that the sum of the torques now has to be I alpha. That's the Newton's third law. So when we go from forces to kinematics to motion, we use F equals ma, because A is a motion thing and F is a forces thing, right? When we do it for rotating things, we obviously have to use torque, but then we're going to get some angular acceleration, which is fine. We could worry about that later. So what are the sum of the torques on it? Well, the only torque is this one, and it has a well, the angle between them, so you could write this as RF sine theta, right? And the angle between them is 90 degrees, so that's 1. And so it could just be R times F, so it's going to be R times T. Does that make sense? This is the torque, the sum of the torques. There's only one, but the torque due to this force is R times T. Does that make sense? I just used RF sine theta. R is the distance from the rotation to the point where it's applied, which is R, radius. F is the force, which is T. And then sine theta it's 90 degrees. So most of these problems you'll have, like when you have things on a wheel, they're always 90 degrees, right, from the rotation. So, okay, so then we get that, and then that's going to have to be equal to I, which now we can fill in. Well, it's a disk. So it's going to have to be this, right, times alpha, which is the angular acceleration. And now we can actually, now we have these two equations. Okay, these are the two equations of motion, right? Now we have two equations, and how many unknowns do we have? Well, the only T is an unknown, right? And so is A. Right, and on here we have T is an unknown here, but so is alpha. So we actually have 3 unknowns in these 2 equations. Now, of course, we have n equations and m unknowns where m is greater than n. That's impossible. So we can't solve these. But we're going to have the same situation as we had before, where this A, if this accelerates with some acceleration A, this alpha has to be related, right? It's literally the angular acceleration of the wheel, and because they're connected by a rope, we know that these must be related. And so we could do the same exact thing we did before, where we know that alpha is A over R. Right. That's the definition of angular acceleration, but we know that basically this is the statement is that the acceleration, the linear acceleration of the block, because it's connected by a rope, must be the tangential acceleration. and tangential is related to angular by this equation. This is always true for, right? The last one is be like x or whatever equals theta over. Oh wait, sorry, that's not right. It's theta equals over r. So these equations take you from tangential motion to angular motion, and whenever things are connected, that's literally what you're saying is that the block falling or whatever is the tangential component basically. And so we can replace alpha with a over r, and that's the same as this a. So so we get r t is 1/2 m disk r squared a over r, so this cancels one of those, and actually the r cancels, all the r's cancel, which I don't really know what that, I guess that makes sense. Well, actually no, I don't think it doesn't make sense. I'm sure it makes sense, I just don't know how to explain it easily, is what I'm saying. So anyway, then we get t is just equal to 1/2 m disk a. Well, that's kind of interesting. Now, of course, if we had something else with the t, if these didn't cancel, we could just divide everything. Somehow we get t by itself, but now we could just literally fill in t right here. And we get ma, so I'm filling in this now for t, and again, let's just say before I plug it in, we'll say why I know I can do that now. Because we have this equation has two unknowns, t and a, and this equation has also two unknowns, t and a. It's the same one. So of course, if we solve for one and plug into the other, we should get whatever we want. Now, I don't want to solve for a. I don't want to plug in a because then we won't have it in our equation, right? If I solve for a, then I plug in, we don't have any a's, and I don't actually care about t, right? I don't care what it is. Maybe they'll ask you, but for now, I actually want to know about the motion a. So I'll solve for t, which is already done for me, and plug it in here, so we get m disk a. It's the same a minus mg. So remember, this m is the block, and this is the disk. Now, let's get all the a's on one side. Actually, first what I'm going to do, so now I'm just doing algebra, but I'm going to divide everything by m of the block. So I can erase these, and of course then I'm going to need to put an m here. Okay. And now I'm going to move everything over so I get a minus 1/2, and I'll have m disk over m a is minus g, I guess. It's kind of weird, and now I want to isolate a. Okay, I'm going to start going up here now. So I give a 1 minus 1/2 m disk over m, right, is minus g, right? So I just factored out a. And then I have a, and of course I want to solve for a, so I can do a is minus g over 1 minus 1/2 m disk over m. Okay. Now this is how are we doing with this, right? Now let's remember before I was saying think about things in terms of limits. When you get a weird answer, there's a perfect case of doing that. Let's say, what if the mass of the disk went to 0? So let's look at the picture and think, what should happen when the mass of the disk goes to 0? What we had is a block connected to a disk that was like unwinding. If this is a massless disk, we should just kind of expect the block to just fall, right? Because it's just like something falling on its own, right? If there's no mass here, the moment of inertia is 0, and so it's like it's not even connected. It's like if you cut it, that would be like setting the mass to 0. Well, if the mass of the disk went to 0, we get a 0 here, and we get minus g over 1, which is minus g, and a is minus g. It's exactly right. It's something falling with nothing. Now, what if the mass of the disk went to infinity, right? So you have a really, really, really heavy disk, okay? And whatever the block is not that heavy compared to the disk, okay? Well, I shouldn't be saying light and heavy. I should be saying relative to the block, right? So now I'm taking the case where m disk, really it's m disk, is much heavier than m of the block. That means that this fraction is very big. That means that we get a very big negative number down here, okay? Okay. That should be positive. Anyway, whatever. We get a very big negative number. No, sorry. Yeah, that's fine. That's fine. We get a very big, yeah. And then we get minus g over a big number, and it ends up being close to 0, which makes perfect sense again. Actually, I'm a little bothered. Okay. Anyway, for some reason I'm a little bothered by this. I still want it to be negative. It should never be positive, right? Because it can never go up. Okay, whatever. There's some, maybe you could rearrange it and it'd be more clear. But anyway, so at least those naive limits kind of make sense. And that's it. That's the acceleration of the block. Now, if we want to convert it back to the angular acceleration of the wheel, which we never really do because it's not a very helpful answer. But we would just have to use this, and we just divide this by r, put an r down here, right? And that would be something. Now, that's all fine. Now that's actually kind of complicated. I actually want to do an easier one first. So let's do an easier one, which is 2 blocks, which doesn't sound easier, but I'm going to make this thing massless. Okay, so is that okay if I erase? All right. So now I want to do 2 blocks on both sides. Now this is a perfect example of, I don't think this was in that quiz that you took twice now, but this should be in one because I actually think there's different intuitions that I've noticed people have. Remember when I took physics, I had this one intuition that was wrong, which is I thought that if you put a block here and a block here, and this one had a mass m1 and this one had a mass m2, I thought, well, if they're equal, of course they'll just stay there, or nothing should happen. That is true. But I thought, well, if m2 is bigger than m1, then it should be the same, it should behave the same as if you had just one block on this side with mass m2 minus m1. Because I thought, well, some of it will cancel, right? But of course, assuming this is massless, this one will just fall with acceleration g, because it's just a block with assuming there's nothing here, right? This is just massless. This one will not. If you can kind of intuit, imagine what's going to happen. Something's going to happen, but it's not going to just fall with acceleration g, right? And why is that though? Because I kind of thought this was and maybe again I don't want to get into the pattern of pretending you have the same intuition as me. Some of us do that, but I actually had this intuition where I thought, well, some of it's like it cancels. It'll cancel the m mass, but so I'll tell you that. I'll spoil the ending, which is that it's not true, but it's not true because remember what I was saying, it might have been different people here, but what I was saying about how gravity affects you proportional to your mass, right? It pulls you, the force of gravity is stronger if you're heavier, but gravity also has to accelerate you, which by Newton's law is proportional to also your inertial mass.
Yeah, I was here if that was the bottle.
Yeah. So your inertial mass is the same as your gravitational mass. Now that's a statement about high energy physics that you don't worry about it. No one really knows what that means, but what that's saying is that this example, we have this much mass being pulled toward the Earth. That's correct. That is correct that the forces, we have some force here, m1g, let me erase I don't want to get it messy. So I will start writing things that are correct now, which is that we have m1g going down this way, and we have m2g going down this way. Now, if we just write this as like 2 things pulling against each other, they do actually cancel somewhat. And they actually give you a net force on this wheel, I guess you would say. So this is technically, I should be drawing the Fruit diagram for the wheel, but whatever. We actually get m2 minus m1g, assuming m2 is greater than m1, right? Shouldn't erase that. Yeah. So we actually will get the same force as this, but if you actually had this situation, how much inertia how does gravity need to accelerate? Only this much. In this case, how much inertia does gravity need to accelerate? It needs to bring this one up and this one down. it actually needs this much mass to accelerate. So in this case, they're not equal anymore. Remember, so in every case, why does everything fall at g? The reason is because the amount of mass that is helping you with gravity is equal to the amount of mass you need to accelerate, which is that's sort of a statement about objects, right? It has the same amount of mass. It needs to accelerate all the mass. In this case, we have some smaller amount of gravitational force, but it's not that you need to only accelerate a smaller amount of mass. You actually need to accelerate the whole mass, the total mass. M total. So we can actually, so this problem, I've sort of already done it, but we can find, let's say, so now we can draw the free body diagrams for the two things separately. They're just going to be like T1, T2. It's going to be sort of simple. It's not going to be that complicated. But if we just draw the free body diagram for the massless wheel, now they're both going to have R's in them because they're torques. They're just going to cancel. So it ends up being like a sum of the forces problem. It's actually sum of the torques, but again, it's just everything has an R in it, so you can just cancel it. But anyway, on this way you get, I'll do it, so this is a shortcut, but I'll do it step by step, which is that way we have minus m1g, right, force, is going to the left. And we also have another force, m2g, going to the right. So this is the net force. Okay, now by Newton's law, net force equals ma, where m is the mass is the total mass of the system. M is m1 plus m2, right? Now let's factor out a g here, just to, we'll see that of course it's just the same as what I wrote over there, but equals this, right? And now if we solve for a, what do we get? M2 minus m1 over m2 plus m1 times g. If you have a simple, I think it's called a simple Atwood's machine, something where the wheel has no mass, this is always the answer. Again, don't, as I usually say, don't memorize it. But you should see that we actually got kind of a weird result. Like this is kind of a weird fraction that we don't usually see. We got it just from summing the forces and then using Newton's law. We've been doing that for a while. We actually didn't even use any rotational stuff. Right, and you can kind of imagine why didn't we use rotational stuff? Well, we didn't have any objects that were rotating. Now the wheel was rotating, but it doesn't have any mass, so we don't actually have to consider it. So that's why we didn't have to use any rotational stuff. And for the torques on it, well, we can just treat it as like it's like a tug of war between two forces, right? Technically there's tensions, but they're all going to sort of, basically we're going to have, each block has mg and a different tension, and then we're going to be adding the tensions, but they're going to be equals to mg anyway, so we can just write it like this. But
So that's the acceleration of the wheel.
this is the acceleration of the wheel. Now let's do the same thing with the limits. Now I already said, well, what if they're equal? If they're equal, what should the acceleration be? If they're two equal masses, 0, that works, right? What if m1 is m1 is like 0? M1 goes to 0, what should we get? Well, that's just like cutting one of the strings. The other one should just fall straight to the ground. We would just get m2g over m2, right? If this was 0, that cancels and we just get g.
Yeah.
Perfect. Now, what if m2 went to 0? Now, you might think that's the same thing. But if m2 went to 0, it would accelerate the other way, to the left. And in fact, if we send these to 0, we get minus m1 over m1, which is minus g, which is the other way, to the left. Because I didn't mention this, but I guess I didn't mention it. Because I called this one positive, I was calling this way the positive direction, and that way the negative direction. So that's why so you might get, if you get a sign wrong, it's not even going to affect your results really at all, because it's just a convention. But I'll do one quick thing. What if we put this block over here? It's a silly thing to do, but if we just put this block over here, what would actually change? Well, what would actually change is that this would just change its sign. And that's actually it, that's it. The total mass is the same, MA is the same. Sum of the forces is just plus this plus this, that would just make this, but now these just cancel, we get A as G, which just makes sense because we're just, again, it's just something falling. So it makes sense in all of these. This is the real case, but anyway. So does that make sense? Yeah.
Finding angular, like the angular acceleration of the pulley, is that
Yes, so once we have A, so if we have this system with
Yeah.
no, again, this has no mass. Well, we can do it with mass in a second, but you can just use this. Right, so divide this by R, 1 over R or whatever. Yeah, and so this acceleration is always true, no matter what, this doesn't have any R's in it, so it doesn't matter what size the pulley is. But you could imagine that, well, you have some system that's going to accelerate a certain amount, but if you have a really, really small pulley, it's obviously going to spin really fast, right? Now, the tangential acceleration is going to be the same, but if it's really small, it's going to spin faster, and if it's huge, it's obviously going to spin a lot slower. And we can see that by, if we solve for alpha, which is A over R, so this is going to be, this is how we'd fix it, right? If we wanted to do alpha. If we set R to 0, which means really small, we get a really huge angular acceleration. That makes sense, right? If we have a really big pulley, big R, that reduces by alpha. Now, you might need to solve for alpha for a problem, but it's sort of a little less intuitive what alpha means. Because A is sort of obvious, you can see when it's G and stuff, but like, we can't really do limits. I mean, we can do limits, but we can't really do limits with G because we don't really know what it should be. It doesn't depend on the size.
so like so you just always use the larger one as M2?
No, you don't have to. I mean, this would still work if M1 was bigger than M2. Because if M1 was bigger than M2, then, like, nowhere did I actually say that, sorry. Somewhere I did say that. This doesn't have to be true because then this would just be a negative number. But that's fine because it would just be going that way, right?
Yeah,
If
so
M1,
you'd just be switching the directions.
exactly.
Okay.
All these equations, I shouldn't have written that. All these equations are true if M1 is bigger.
Either way.
Yeah, because then if M1 was bigger, we would get generally a negative number,
Yeah.
which is fine. It means it tells us go to the left. Yeah.
Okay.
Yeah. Now, what if we? Now, at the risk of, I don't want to just keep doing things way too fast, so I'll stop after this. But I just want to say one more thing. What if this had mass? Which is sort of like I don't want to say the hardest problem, but this is one of the hardest types of problems probably in this semester. So if you can do this, I would not worry as much. But I mean, you don't expect to do it right the second because you've seen it like for 23 hours now or something. So, but if this has mass, well, what changes? Right? Well, we actually can't use force anymore. Because remember, if we talk about the forces on a wheel, well, the forces don't actually mean anything on their own. The torques mean something. So we would actually have to change basically this line. So everything we did right there, M1, M2, that's all fine. And I'll use big M, capital M for the mass of the wheel. So, all right, I'm gonna erase. Is that okay if I erase this? Right. So now we're going to use the sum of the torques has to be what? Well, that's just I alpha, right? That's this. So you basically always just write this. If you write this, you will be guided in the right direction. So because something's rotating. Now, if I was being very, very careful, we really should have written this for the previous problem. Like I said, in this case, it doesn't matter. It's the same thing. But if you want to be very careful, you should always assume that you have to do torques when you're having something rotating. So what do we have? Well, we have a torque. So now this is the sum of the torques on the rotating thing. We could write the free body diagram, whatever. What we really want to write is actually let me do the free body diagrams for all the three. So in here we have, I'm not going to draw them separate just because I don't want to. But this is going to be the free body diagram for here is going to be. So for mass 1, we're going to have T1 minus M1G is, and this is going to be, the sum of the forces is M1A, right? I'll say A1 for now because it's the acceleration of 1. Okay? Actually, we don't even, I was going to do that and then show you that they're the same, but it's sort of obvious that whatever the acceleration of this is, this has to have the minus acceleration, right? Because they're connected. So mass 2, what's the free body diagram? Well, now if we called this way positive, right? Like this way is positive, then this is actually positive direction, right? This gravity is actually positive now because anything going this way is positive, right? This is actually just a convention, but it's easier just to treat everything as like sort of a rotational kind of thing. So we get M2G minus T2 is M2A, and now this is the same A, and they're the same direction, right? Because remember, because I use the fact that everything going this way is positive, if this has a positive acceleration, this must have a positive acceleration. Or they could both be negative, but they have the same sign. So the fact that I switched the sign of this is reflected in the fact that I'm calling acceleration all like one direction as well as positive acceleration. Anyway, so we have this. So we have three. We have three unknowns so far. We have T1, T2, and A. Okay, so we better have another equation that doesn't have any new unknowns in it. So what do we get? Well, what's the sum of the torques? Well, at this point, we have a torque going in the negative direction because it wants to pull us that way, right? It wants to rotate us this way. And so we have a negative T1, and now R is the radius, and they're always perpendicular, so it's just that. The other one is very similar. It's just positive T2 R, right? So this is just torque is R cross F, or RF sine theta. Again, as usual, these problems, sine theta is 90, so or sine theta is 1, I mean. And so we have T times R. R is just a constant. T is the unknowns from up there. And then that's it. There's no more torques on it. There's only two torques. They have opposite signs. Very important. So,
wait, why is T1 negative?
so T1 is the one that's going this way, and T2 is going this way.
Oh, because it's
sorry.
about the disk.
Yes,
okay.
sorry.
Okay.
This is for, I should have written disk here.
Okay.
So tensions like act inward, right? So on the disk, it's actually in the opposite direction of the
Yeah.
That's a good question though. And now this must be I alpha, and now I we can just fill in 1/2 m r squared times alpha. And now we again, because I've written, as soon as you write a new variable, you should immediately wonder, I hope nothing's going to go wrong, which is that I wrote an alpha, and that's the fourth variable. We have three equations, we have four variables, we definitely don't want this, but of course we can always convert this alpha to be related to that A that we've already been talking about. So we can talk, this is alpha over, oh wait, no, A over R. I always forget. So here's by the way, a way you can remember. A equals R alpha, V equals R omega, and X is R theta. You can remember the R goes with the Greek letter. Because I always forget, like, I always think, oh, maybe it's RA is alpha or something like that. No. So anyway, the R always goes with the Greek letter to multiply. Often you need to put the R under to actually use it, but this is how I remember it. And remember, when I say A, V, and X, I'm talking about the tangential, which is, in this case, it is, in fact, the tangential we need. So, great. And so actually, one of the R's cancels here, I guess. Actually, no, they both cancel. That's kind of weird. So we had an R squared here, and we divided by R to get A, and we also had an R everywhere on every term, so we can cancel that. And we get minus T1 plus T2 is 1/2 m A. This kind of looks similar. We had a very similar thing a second ago with a single block. Okay. Yeah. And now we have the unknown, so it's very clear that there's three unknowns and one of them we care about, A. The other ones we don't care about. We don't need to solve for them, we don't need to write them anywhere. They could ask you about them, which in this case, if we have the answer, we could just plug back in anywhere. But basically what we want to do is solve for T1, plug in T1, we get A. And plug in T2, and we get T2 is M2G plus M2A, because it's the same. Wait. No, minus, sorry. I was wondering. Okay, and this has to equal 1/2 MA. Now we have three things with A's in them, and a bunch of stuff that doesn't. We probably want to take everything with A and remove it. So all I did was now we basically, the moral of the story, which is not the actual end of it, is that this equation and these two equations, we had three objects in this system. Three objects that were all sort of interacting, three free body diagrams. Each free body diagram led us to whether it was a rotating object or a linear moving object. We could either say that the sum of the forces is Ma or that the sum of the torques is I alpha. And using those, we get a system of equations. Okay? Once we have the system of equations, everything else is just solving for whatever we need to. That is not the hard part. I mean, not that it's not, you won't make mistakes. You often make mistakes. But that's not the part that's actually important. Once we get these three, the physics is here, we just need to rearrange things. It's rearranging is really what so yeah. So does that make sense how I got these three equations? Okay. I'm just trying to see if there's an easier way to, I guess we just have to kind of do it. So 1/2 MA plus M1A minus M2A. So I've just taken everything with the A's and, yeah. Oh, sorry, this should be plus 2. Because I'm moving everything over here, basically. And then this would be this side, which is minus M1G plus M2G, okay? And now we want to factor out the A. I'll do it in one step, even though I'm probably going to make a mistake. So I want to factor out the A and divide by everything. So that would be minus M1 plus M2G over, and now it's everything multiplied to A, which is 1/2 M plus M1 plus M2. Oh, look at that. Okay. So hopefully I didn't mess anything up. All right, and so now let's do some limits. Well, if we have the same thing on the top that we had before, where if we take one of the masses be much heavier than the other, we get either G or minus G, right? One goes to 0 compared to the other, really. If we get G or minus G, that's good. Actually, well, no, we don't quite. No, sorry, we don't do that. If we had the expressions for the acceleration, I forgot what they were. The ones we did before, where if one of the masses didn't exist, if we take M1 to be 0, we should, hopefully that was the same thing I wrote before. I don't really remember. Yeah, I believe it was if you multiplied over the top and bottom by M or something. But hopefully it would be the same thing. Basically, if this system is, if it's bigger than another system, if it has an extra piece, just take that mass of that piece to 0 and you should get the previous system. So assuming if you do like on a test or whatever, and you have like another problem where you have to do this system and another system with just one, or with this massless or whatever, we can take this, okay, take the mass of this to 0, and that was definitely what we had a second ago, right, with the massless wheel. So just take M0. What else if you take, so the thing I was saying is that if you take one of the masses to be much bigger than the other, it doesn't actually go back to G or minus G. I shouldn't have said that. That's wrong because there's still the mass of the wheel, right? Even if you take one to be very, very small, it doesn't act like, it's not like something falling because the mass of the wheel, it just acts like something with a single wheel and nothing else, right? And so anyway, so that's, you can see that, how that would work. You can specifically see here the thing I was saying at the very beginning when I first started, which is that the acceleration, the momentum, not momentum, the inertia that it has to overcome is the sum of all the masses, but the forces it receives, which is sort of at the top, if you think of A as F over M, right? The inertia is the sum of everything, and the forces are, you subtract them because they're acting against each other. So that was what the thing I was saying about, it's kind of like they sort of cancel somewhat. They do in the sense that the forces do actually cancel, right? The only things providing forces are the gravity forces of the two masses, and they cancel, as in cancel meaning they subtract, like they partially cancel, I should say. Whereas they still have to accelerate a mass that's actually the sum of them. They don't cancel; those things don't cancel; they add. Because you have to. Not only do we have to accelerate the mass, but we also have to accelerate the wheel. And it turns out that that because we had a disk, it just happened to be that the moment of inertia interval type thing. It happens to be that 1/2 of the mass contributes. So it's as if we had another mass sitting there with 1/2 of the mass of the wheel. That actually would behave the same. Well, it wouldn't quite because we don't have the gravity. But anyway, whatever. I guess you could say, so this is going a little beyond what you need to know or for anything, but this, we could say that this behaves the same as a system with M1 M2. So there's two blocks, and this is like a table. So it's like you hung two blocks off a table, and on top you put another block connected to that with a mass of 1/2 of the mass of the pulley. That would literally be the same exact formula. In other words, that mass on top doesn't contribute at all to forces because there's no gravity on it, and assuming there's no friction. But it does. It does contribute to the total mass. You have to accelerate it. So that doesn't really help you with anything. But I suppose you could imagine the situation is like that. If you're having trouble visualizing what would happen with the three masses, it's kind of complicated. It'd be the same as that system. Does that make sense?
Yeah.
So the concepts we actually used are not, there's not that many. It's not, it looks like we used a lot, but all we did was use the sum of the forces is MA for each object separately for all the free body diagrams we had. Basically, we had three free body diagrams. We used F equals MA for all of them, except for the rotating one, we had to use I alpha. And once we have that, and using the relation between alpha and A, we have three unknowns now. And two of the unknowns are, I guess you can call them internal. The tensions are sort of internal, meaning you could measure them, but you'd have to do a lot of work to measure them. In other words, we don't really care about them. We really do care about A. Now, of course, now that we have A, we can actually, solve it for a specific, like a number. We can actually plug back in anywhere and get the tensions if we really want to. So if they ask for the tensions, you could do that. But it's not like, hopefully this is still recording. Yeah, it looks good. Okay, and you could solve for any variables you want. But okay. So that was, hopefully that kind of answers some of these problems. I assume these homework problems are going to be like basically this.
Could you go over
Yeah.
this question?
Yes, this one.
The right hand rule confuses me.
Right. So consider pulling that string. Oh, I see. Oh, yeah. This is gonna be okay. So let me erase this. The right hand rule. Yes. Yes, that is. Okay. Select the point of contact between yo-yo and the tables. The point take torques around. Yeah, so that statement means we could take torques around any point, but the only torque is due to the tension of the string since normal and frictional force pass through the point of contact. Yes. The direction of torque on the yo-yo due to yes. Okay, so A has. Let me actually write them. T, and then another one we have.
Yeah,
And then
these are all those. Yeah.
T, and then another one we have. On here. T. Okay, well, because they're using. Well, when they. Yeah, so there's friction and normal. So at this point, there's a bunch of forces applied, right? There's normal forces in gravity, and there's also friction because, assuming the surface has friction, if this wants to start turning, of course, if a thing wants to start turning against something else, that's sliding, it's friction, right?
Yeah.
So you would get some friction. So if you, let's actually imagine this one. Let's just imagine, not necessarily do any computations for right now. Imagine this one. Well, what's actually gonna happen? Assume this has friction. That's like normal everyday experience. If you try to pull this, well, it's gonna want to go this way, right?
Yeah.
But of course, it's not going to. If you assume it doesn't slip, it's not going to. Why is it not going to? It's going to because it receives a force, a torque this way, right? And a torque this way must be applied by a friction force this way. Does that make sense?
Yeah.
Wait. Yeah. Wait. Okay. Hold on. Let me take it.
Because
It's
it's like
rolling.
the oh,
Wait. Okay. Well, let me draw another one because. Well, hold on. Let me draw this. So if we have a tension force, we're pulling this. This is going to want to make it go this way, right? And if it doesn't want to slide, so you must have a friction force turning it back this way. And so this must be this way, right? Does that make sense?
the friction force that way.
The friction force, yeah.
So it can roll.
So it can roll. Because if it didn't have this friction force, it would want to turn this way. Oh, wait, hold on. Okay, hold on. I'm confusing myself. Okay. So, if we have this, we have a torque going this way, right?
Mm-hmm.
Now, this is not the actual vector of the torque. I'll talk about that's right hand roll, but I'll talk about the same. So therefore, we need a counter torque. Yeah, around this point. Yeah, around the center. So therefore, we need a counter torque going this way, which means we need to apply a friction force like that.
Doesn't friction like oppose the motion though?
Yes, the motion of the bottom of the wheel is going that way, right? Right. So the center of mass is moving whatever.
Okay.
But the bottom of the wheel wants to go. If there was no friction, it would want to go that way.
Okay.
So the friction force opposes the motion of the contact.
Yeah.
Does that make sense? So now this one, so I believe that is right. So this one, now you're applying it, they specifically drew this underneath the center, meaning this is applying a torque this way, therefore the friction torque must be that way to oppose the motion. The force is going to want to rotate it like that. Now, yeah, that's it. Now, the other thing is that this, because it's not, now what we've been working with the things, blocks on wheels or whatever, is torques that are exactly perpendicular, and we don't care about the center of mass motion. But generally, when we draw like something like this, This is not like a perfect torque, right? This actually, it's true that the sum of the forces on this are ma for the center of mass, and the sum of the torques are I alpha. So when something's rolling and so rolling involves both of these, right? Rolling involves something moving and rotating. Okay, now rolling without slipping would be the same thing I was saying before, which is that condition, that A and alpha are related by the radius. But they're separately important. So this is a force on the center of mass, and so is friction, right? Now friction, if it's going to roll, friction can't be as big of a force as this one. Because imagine, so the only forces on this in the horizontal direction are this tension pulling and this friction force. If these were exactly equal, this wouldn't move. Okay, forget about rotation. The actual forces on the object, if there's no more horizontal force on the object, the sum of the horizontal forces still has to be the horizontal acceleration. Always, that's always just true. Okay, and you don't you can say all this stuff about rotation. Doesn't matter. It's not going to move. Everything we learned before about linear motion is still true. It's not like it's not true when things rotate, right? It's still true. The torque, though, we also have to consider. This also exerts a torque, right? It seems like we're counting something twice, but we're really not because these are separate conditions, right? We're not adding them or anything. This also exerts a torque, and this exerts a torque, and now everything at the center, around the center, and everything at the center doesn't. Like the gravity doesn't have a torque because it's sort of symmetric. But this also has to be true. So this is actually two separate conditions, right? And then you can kind of replace them with one variable, which is if they're rolling without slipping. But okay, now we don't have to use that for these problems because they just want you to describe them, I think, right? Or they want you to find the direction. So we can do the direction, which we haven't done yet. So the actual direction of torque. So when you
the direction of angular acceleration.
Yeah. So
Force the torque is the angular acceleration since it's the force
Yes.
about the sun. Okay.
because I is a scale, it's another vector. Yeah, so the direction of torque is the direction of angular acceleration, the net torque, right? This is the
Okay.
net. So in other words, if for this problem they want you to imagine it.
Okay.
What if I did this? What if I pulled this up? What would happen? Now, yes, there's going to be some friction stuff, but what's going to happen is it's going to go like that.
Yeah.
So now so the torque is going to be like this way. Therefore, it's going to be out of the page.
Right.
So using the right hand, if something goes this way, it's out of the page, which is you can write it like that. It's a circle with a dot in it. That's a vector. This is an actual vector. Vectors can't be curved. That's never a thing. You can draw the motion for a helpful thing, but an actual vector is a straight line, right? This means a thing coming at you. Now, if something was going to rotate this way, by the right hand roll, our thumb would point it into the board. This is like the back of it. It's supposed to look like when you draw an arrow. What if you looked at it from the front? You would see that, I guess.
Mm-hmm.
And if you looked at it from the back, you would see if it was an actual arrow, you would see that. Anyway, it's a little silly, but that's this is actually how you draw it. So if you want to draw the three axes, this is the y-axis, this is the x-axis, and then that is the z-axis. Now we usually draw it at an angle because it looks nicer, but this is technically how you draw it. Now I don't really care if you if you write the words out of the page, it's actually probably a little better because it's less ambiguous. I don't care either way, but you can never be wrong if you write the words out of the page. So in this case, the torque, the net torque, yes, there's going to be friction. It's going to want to turn this way, so therefore there's going to be friction this way, right? But the friction's never going to be greater than this force, right? They could be equal, they could cancel, and it won't move, but the friction can't be bigger than right? Because it's not going to, the things don't move on their own. The friction can't be. So it's going to want to turn this way. So what I would do is imagine what way would it turn?
Why does it want to turn that way? Because it's on the right side of that.
Yeah, let me draw it a little more exaggerated. Yeah, just basically what I would do is imagine what it would be like to pick something up like this. Don't worry about the calculations or anything, but just imagine if I picked something up from the side, what would it want to do? It would want to go that way, right? And if something wanted to go this way, make your right hand fingers go in that direction, right? And then your thumb would be that one. So this would be torque is out of the page in this example. So if you curl so it wants to go
Okay.
that way, and curl your right hand fingers there, and then your thumb would go out of the page. So the torques for all these have to be out or into the page. It's one or the other, because it's perpendicular to everything on this plane. The torque vector.
So that one is going out of the page too.
Yes, because if you pull like the bottom, it's going to want to roll this way like that. So that's out of the page, yeah.
Okay.
One's also on the right.
Well, actually, hold on.
This is just because it's a little bit to the right.
What? This one you're talking about?
Yeah.
Yeah. So they show that it's supposed to be like a little bit off here, and yeah, so it's going to want to rotate like that way around the center, kind of, and therefore it's also out of the page, I guess. I believe though they specify. So I should have read this more carefully. They say that they're talking about the point of contact is where they want to take the torques around. Okay?
Yeah, and what direction will the yo-yo move in?
Right. So now, forget about. So remember, I was talking about the friction force. That's important, and that's true. And when we talk about the sum of the forces, we have to actually talk about all the forces. They say in that example, we don't want to worry about the forces at this point. So let's talk about that as the point of rotation. Now that's fine, but a lot of problems will involve both of these, and you can't just ignore things. Often you can. Well, I'll get to that, but. So if we talk about this as our point of torque, our answers may be different, right? If this is our point of torque, then this force of friction has how much torque associated with it around this point? 0, right? Because it's r f sine theta. What's r? R is the distance between the point we're talking about and where the force is applied. So the point we're talking about where we want to measure the forces is here. The point where the force is applied is also here, so r is 0. When we were talking about before, what we were just saying is I was thinking about this point. Now it would be this distance here. The point we're talking about is r. Sorry, the point we're talking about is here. The point the force is applied is here. This distance is the radius r, whatever. So that would be how we calculate the torque. So generally, so what his point was at the end of class about picking the point where the torque is. If something's not rotating, so if you've taken like class statics, there's a class called statics. I've never done such a thing, but from what I've heard, it involves a lot of things that are not moving.
You could tutor
I don't know about.
it.
We'll see. We'll see.
You can do it, of course.
If you have a bunch of whatever things are, I don't know, whatever objects, assume they're all touching, then if nothing's rotating, okay, if nothing's moving and nothing's rotating, that means that the sum of all the forces of every object must be 0, right? And if nothing's rotating, the sum of all the torques around any point is 0, right? If something could be rotating like this, well then, yes, you have to worry about the torque because it could be non-zero. But if, like, for example, in this, you might think, well, nothing's rotating, so how can I use torque? Well, if you can, you just say that the sum of the torques is 0. That means not rotating. So anything like, often there'll be a problem where there'll be like a pole, and then actually here's a good example that I bet you will have a problem like this at some point. You have like a rod and like a string here with a tension, and it's holding onto another rod that's like fixed here. You've seen
that
it?
in static.
Oh yeah, there you go. And now you can talk about some of the forces, all that stuff, and you need to actually, but you also need to talk about the sum of the torques, because the sum of the torques of this, so this rod can go up and down. It has a moment of inertia of 1/3 mL squared, right? The sum of the torques around this point is 0 because this rod is not rotating. And that's very important because there is a normal force. There's a force this and there's a normal force here exerted from this rod to this rod. That's very complicated. I don't know what it is. It's actually really hard to find out what it is. It involves the torque around this point. But anyway, that's really hard to figure out. And so if we set that as our rotation point, we can find the sum of the torques around that point, I'll call it A, is 0, and therefore now I know this is well, it doesn't even, I don't even need to know the moment of inertia of the rod, but now I could say, well, there's some, center of mass. You treat this as the center of mass, and you say it has some force times r like this, and then you have this is some component goes up, and anyway, we can talk about that. Anyway, so the point that he was making that's actually really important for these types of problems, not necessarily these yo-yo things, but is that if you have a thing where things are not rotating, then the sum of the torques around each point separately is 0. So you actually have like infinitely many of these equations. You only have one of these because, well, you have as many of these as you have objects, basically. So you could do this for the rod. I guess the string is not really, I guess you could talk about the sum of the forces on the string, but you probably have, so like we just did before with the wheel and the 2 blocks, we have 3 objects, so we have 3 equations of motion, like this. For this, we could actually have a bunch of equations of motion for like a statics problem, right? So you've probably seen these before, right? So you could have a bunch of, so he was really trying to make that point because it actually is really important that if you don't know about the force somewhere, like for example, we don't actually know about the friction here. In this example, we know that it exists and we know what direction it is, but we don't know anything about the strength or what causes it or whatever, right? Or, I mean, yeah. So what we could pick is this is the torque point. So all the torque around this point is what we care about, and therefore we don't have to worry about this. We actually also don't have to worry about gravity or normal force. We didn't here either because they were above the center. But if we're talking about the torque around this point, we also could. It's still valid. There is still a torque. It might be 0. I don't know. It actually won't be if it's rotating. But then the torque of gravity would be non-zero, and that'd be really complicated. So and normal force would be non-zero as well. And this would be it would just be really complicated. So and also we have something rotating not around its center like a disk, and then we have to use the parallel axis theorem and the whole thing. So we probably won't do that. But in this case, they want to talk about the torque around this point, and so we have this, and so the torque should be where? Well, around this point, it wants to rotate that way, right? And don't think about like, well, it can't really because it can't go through the floor. Just think about the instantaneous rotation. Well, you could think about the alpha and the torque, the direction as like, where would it instantaneously want to go? In like just an instant, it would sort of want to rotate like this way around this point. So using our right-hand rule, it would want to go that way, right? And therefore the torque at this point would be inward, toward the board, in the board, right? And then for this one, this up here relative to this point, this is going to want to rotate it that way, right? And so if we use the right-hand rule, it's going to be out of the board, right? Yeah. Yeah. And for this one, well, this is applied right at the point. So this is going to induce.
Oh.
Yeah. So they're saying at this point, at the point of contact, if you apply a force there, just like friction and gravity and all that stuff. Well, not gravity, but the normal force. There's no torque associated with it because the r is 0. So this doesn't make it want to rotate at all. It's a little misleading. Well, it's not misleading, but it's confusing that they put this vector through the thing. I mean,
It's tangent to it.
All it means is that it's applied at this point.
Yeah.
It's not actually going anywhere. Like vectors don't go anywhere. They're just applied to a single point. They just draw them to show their length and stuff. But this is just like this is like saying you're pushing on a door right at the hinge, right? You can go literally any direction. It does not matter. You will not open the door at all because it's at the hinge. So the radius is 0. So there's many ways you could push on a door that would not cause a torque, which like pushing, like if the door was here and you're pushing in toward it, that would not cause a torque, obviously. But also if you push any direction right at this hinge, it would not cause a torque. And that's what this is saying. So you could make this vector any direction. You could do this, you could do this. And because you're applying it right, you're saying, what's the torque on this wheel around this point? How is it going to rotate around this point if I apply it at this point? Well, it's never going to rotate around that point if you apply it there. It might rotate around the center, right? But we don't care. We're saying what torque is around this point. So the thing I was saying about the applying the torque anywhere is that it's very tempting to only ever use torque when things are actually rotating around points. And because it's sort of the most obvious way you think about it, you're like, well, I would take the sum of the torques when something's rotating around a point. But if things aren't rotating at all, then everything's not rotating around everything. So you could sort of vote. So in other words, you might think, well, this is a yo-yo, it's supposed to spin around the center. Well, okay, but it also doesn't spin around this point, or maybe it does a little bit, right? You could talk about the torque around any point, and it has some angular acceleration around every point. It just might be a little more confusing to imagine. But I would use, if you're sort of confused about this, I would just use this formula. Those are literally the only things that torque can possibly depend on. The distance, r is the distance between where you're talking about rotating around, which in this problem they actually tell you is this point. They don't usually tell you, usually you make up your own. This point, and the place where the force is applied, which is also the same point. So if distances are at the same point, the distance is 0. So r is 0, then the whole, you don't even have to do it. But then it's proportional to the force, but it's also proportional to the sine theta. And so, yeah, I guess that's it. I don't know. Well, I was going to say, with this thing, this is a force applied. So if we're talking about the torque around this point on this rod, this is a force applied at the end. So I know it's some length or whatever. So I know r. I know f because it's t. But then I have sine theta because the vector r is like this way, and the vector t is like this way. It's really in here. It's really this angle here, I should say. So you have to take, I'm just extending it so you can see, but so it'd be the sine of this angle. So it wouldn't just be, or you could take the component, which should be t sine theta, right? This is the component in the vertical direction. That would just be, and then they were perpendicular. And it's the same thing.
So the r is 0 for all of these because it's...
The r is 0 for all these for the friction.
Okay.
Because the friction is applied at the point they want you to measure it, measure the torque around.
Okay, so that one moves to the left because it's like going counterclockwise.
So this T, now we're talking about the torque that this T force applies, right? So the torque that this applies is going to be, well, it's going to want to make the disk go this way, right?
Yeah.
Around the center, right? It's gonna, because it's not gonna go like, I'm trying to, well, anyway, it just makes it want to go this way, right? You can kind of imagine that if you pick it, it's gonna go on. So this way is this way around this point, and it goes out of the board, right? We could actually compute the sine theta. So the r vector. So in this case, if we actually had to compute the torque, this is the r vector, right? And this is f. So it would be this times sine of this angle. And it would be positive, which means
So it'd be r times t times the sine of that.
sine of this angle, right? And because this is between 90 and 180, right? And if you look at the sine graph, between 90 and 180 is over here, whatever, so it's positive. So we're going to get positive torque. And positive means that way.
Okay.
Another way you could think of it is, because remember I said that the torque, so if you're having trouble imagining which way this would rotate, because some of them are a little hard, what you can do is, remember that the torque in these, because this is on a plane, the torque has to be either out of the board or into the board. So if I negate one of these things, I should have the opposite torque. So if it might be easier if you imagine the negative, what if I just flip this force around? Then it would clearly roll this way, right? Around this point, it would clearly want to go this way. And if I do that, the torque would go into the board. And so because I negated one thing, I could just flip it over, right? There's only 2 answers in this. I think actually that's a little easier to imagine. If I flip this T downward, it's sort of very easy to imagine that it's going to go like this. This is a little harder to imagine.
Yeah.
But anyway, if you imagine you flip it, well, I know I'm just going to get the opposite torque. It's just like the cross product thing. I mean, it literally is. This is a cross product, right? If you just flip one of them, if you flip this one to like the other side, you flip the. See, that's literally R cross F, and if you just make F negative,
Yeah.
right, which is this or this, if you flip the second one, either one, yeah. So. Okay. 7 gigabytes is the file size right now. Huh. Anyway, okay. Does that make sense? So, you shouldn't feel bad if it's not very intuitive for you,
Yeah.
because it takes a very long time for this type of thing to get. Because you have some intuition about, just like with his little quiz about the car hitting another car and the forces, you have some intuition and you have to adjust a little bit. And for this, you have some strong intuition about, not you, I mean, you do too, but one does, about if you've seen objects in the world, right? You know that things rotate their way, but it's actually very difficult to get your intuition to really understand these, torque around every point. And what about torque around a point that's not rotating around? Does that even make any sense? And yes, it does. It's just sort of a lot harder to imagine. Like this, like another, so it does one more thing. This object that rotates and has forces on it, this has a torque around like this point or whatever. You could just compute it. It's R and F. You could totally, R would just be the vector from here to where the forces are applied. That would be it, because it does have some rotation around this point. It just might be like, it might be 0, or it might be, if it rolls this way or something, it'll be like, it is kind of rotating around this point. So you could, that's what he was, remember when he drew he had some thing and then he drew like a point here,
Yeah.
and he said there's some angular momentum. So the statement that he was trying to say was that every object has angular momentum around every other object. You can always define angular momentum. It's not just if something's rotating. Now, if something's rotating, it's fine, but and it's actually kind of useful because conservation of momentum also applies to angular momentum, and it's actually really sort of well, I won't get into it, but it's a very deep statement about the symmetries of the universe that angular momentum is conserved. And this is a silly example. In this case, you probably wouldn't want to use angular momentum because something's moving in a line. But in fact, the angular momentum, which is r cross p, right, is actually a conserved quantity. It just seems a little weird. You would normally think of angular momentum being conserved as like a wheel spinning. You would say, you add some mass to the wheel or whatever, and the angular momentum is going to be conserved. Or you have two things spinning and you put them in contact, and now it's just conserving momentum, but now it's angular, right? So anyway, okay, good. All right, so hopefully that was some good torque stuff. What are the other? Are the other questions about pulleys?
There's
I
a
thought I.
rope tension question. So that's a little
Okay.
different.
Which one was that?
Number 12.
Yes. What? I don't even understand.
Three-dimensional free body diagram.
I don't actually understand the situation. Is there gravity? If the tension of the rope is something and the collar B is fixed to the bar, the system is in equilibrium. What? Yeah, I genuinely don't understand the jump. Like, is there gravity? Where's the gravity going? If it's going downward at Z, then why is there a tension in the rope? I don't know, maybe there's just is a tension in the rope. All right, I guess you're just supposed to suppose that there's a tension in the rope. So all of the torques are going down. The gravity on the. Let's do. So you see the page. You see the page before where they have 54, where they have a little picture at the top.
Mhm.
That's what I was trying to talk about before. That should be the same problem as this.
Just involves matrices.
Well,
So we have to do some cross products.
oh, they want you to use the inertia tensor. I see. Yeah. Okay. Well, let me just talk about not this one right now because yeah, it's just going to get into a big matrix thing. Is it though? Do you need to do that? I'm sort of a little suspicious. Huh. I'm a little suspicious that you even need to do that. I think you can just do it. I think you can just do it without matrices. I don't know why. I'll look at this and see if you really need to do that. I could do, so I don't want to do that right now because I'm not going to be able to do it very well. I'll look at it and do it on Saturday, and then it'll be on the video too.
Yeah.
But I could do, if you want to do right now, I could look at this one, the one right before it, the 54, page 54. That's the that is the statics problem. So I have a small suspicion that that problem you could actually reduce to this problem. But I'm not going to promise that. So yeah, that was the one where, so we have this, I sort of already do this. We have, now they could just tell you the mass of the bar. You should sort of have to know that the gravity acts in the center of mass, right? mg. And then T, this is 45 degrees. And they have a 500 newtons thing. I'm going to write M1. Oops. M1. Actually, I'll write little m instead. And this is big M is the bar. And little m is the. It's a little confusing because the numbers they give you are not the same. So this is 10 meters long. I hate numbers. I don't want to use. I'm going to use D. They're just so ugly. They don't. Nice. So anyway, and then you have some force here. Now, you could figure out the force here if they asked you to, because the sum of the forces on this is this rod here. I assume it's just a rod, right? I'll call it a rod. This rod is not accelerating, right? And linearly in any direction, right? Doesn't appear so. Yeah. So we could find this force here. I don't know if maybe they want you to do that, or they want you to find, given this force, they want you to find the tension. Whatever. The point is that if we add up all the forces on this rod, we should get 0, right? It's not accelerating. So what are the forces on the rod? Well, we have mg from gravity. This is a block that's on the end. So how does it affect the force? It's still just a force on the rod, right? So it's plus. I guess I should do minus. Sorry. These should be minus because they're down. Right? So those are two downward forces. What are the upward forces? Well, there's a tension force, but of course it's not the regular tension, it's the component. This is not 45 anymore, this is going to be theta. And now we have theta. Now we could The answer is sine of theta. The one they gave you, of course, if it's 45, it doesn't matter. We do sine cosine, but in fact, it's sine. And now, yeah. I guess we would have to do a little more work to find f. Let's just say f is given. Let's just say f is given. F is going to be, I have to introduce another angle. We could find f, but we couldn't find f and t, but at the same time, we would have to choose one or the other. Let's just say, let's say f, so we know somehow it goes up at theta at the same angle. So it's going to be f sine theta. Whatever. I don't really care about that. But there is some force here. Now this must be 0. Okay? And we know that, well, everything, these are known. This is known, and this is, I guess, known. We could solve for t, right? Actually, no, they probably don't want you to do that. Okay, I see. So they don't want you to, okay, we don't know f. Yeah, we don't know f, so we have two unknowns here. So it's we can't solve for t by itself. If we could, then we'd be done, and that would be too easy. So what we can do, though, is say, well, I actually don't care about f. This is not going to be useful, this equation here, because I actually don't know the angle. I really shouldn't have even said this. I should have said some force that's like a normal force, but it's also like a friction force, right? There's a normal, actually we could even break it down into, there's a normal force because this is being pushed into the wall at some point, right? The normal force has to act opposite the, it can only be pushed this way, right? But it's also going to be receiving some friction force, right? So F that they wrote is really these two forces. The friction force can only act parallel to the surface, because in other words, like the rod kind of wants to fall, but it's also kind of being pushed into the thing. So it receives a normal force from that, and it receives a friction force. Now, if you add them together, you can get some net force F, which is what they wrote. The point is that if we talk about the torque around this point, we actually don't care about them at all. So it doesn't matter what we call it. We can torque, friction, whatever, right? And that would be generally very complicated. We could do it. I'll tell you how to do it. We don't have to do it. But what we could do is say, well, this is no good. But what the torques around any point at all is 0, because it's not rotating either. This statement says it's not accelerating. This statement says it's not rotating. Well, again, that's not correct. This statement says it's not accelerating, meaning it could be moving at a constant velocity. It's just not accelerating. This doesn't mean it's not rotating in the same way. This just means it's not accelerating in its rotation. So if something's rotating at a constant velocity, this is still true, because alpha is 0. Alpha 0 could mean that omega is constant, which also means that L is constant, constant angular momentum, just like this means that it's constant momentum. Anyway, so this is conservation of angular momentum for no external torques. Anyway, so the sum of the torques is 0, so what does the torque do to this one? So there's, how many torques are there? There's this one, and there's this one, right? There's no torques here, because again, R is 0. Yeah, R is 0. So we have mg, and now this is the mg. Now, if this distance is d, this is acting at d over 2. Okay, and I'm skipping a few steps because, we don't have to write it down every time. This is the force, this is the r, and there's sine theta, well, it's 90 degrees. Right? R is the vector, technically, from the center to where the force is applied. Not the center, the point that we're considering the torques around and the point where the forces are applied. But, yeah.
R is the difference between where you are and the center of mass?
No, R is the vector from the point where R is from, it's a vector from point that you're considering torque around. This is not going to be grammatical. The point where you're considering the torque around that point. You can pick us wherever you want. And this endpoint is the point where the force is applied.
Okay.
Right? So it's doesn't necessarily have anything to do with the center of mass. And actually in the second part, so the second torque we get, I should write minus because it wants to go sort of, we'll call this way negative. The other one's going to be minus mg, and now the distance is going to be d. And we can see for this one, the r vector was going from here to here, that's distance d. and the vector and center of mass doesn't have anything to do with this r vector in this case, exactly, right? So in this case, r always starts at wherever we're for a given, we're saying the point around, let's say I'll call this point A. I know I'll call it something else point A, but point A. So the r vector always starts at point A for this calculation. If we do another torque calculation, we could pick another point like this one, and then we could actually solve for this torque here. But then anyway, okay, so that's this. So this is this one, that's this one, plus, and now we have the t. So we have t times d times, and now we have an angle now, so we have to use sine theta. These ones had sine theta as 1 because they're perpendicular. And that's it. There's no more torques around point A. So this must be equal to I alpha. Now we can plug in I. It's a rod, and it's now it's important that it's rotating around the end. Now this is where it's a little confusing because it's not actually rotating, right? But because we consider the torque around this end point, the relevant I that we care about is the one of a rod rotating around its end, which is 1/3 m. D is the length now squared, okay, times alpha, right? And alpha, well, no, alpha is fine. We don't have to convert it to A. We could convert it to A using this with R as D, but then we'd be talking about the acceleration of this thing. That's fine, but it's just that it's not obvious that we want to talk about that. Like with the pulleys, it's kind of obvious that the main thing we care about is the acceleration of the blocks. But in this case, maybe we actually cared about the acceleration of the center of mass of the rod. Right? That could be what we would care. I mean, nothing's going to accelerate, but oh, sorry, this is 0. Yeah, what am I talking about? This is 0. Okay, well, this is true if it was accelerating. So if they said it was falling, or let's say they cut this t and this goes away, then it would be equal to this. Sorry, I don't know. I lost track of what we're doing. This is 0 because A is 0, alpha is 0.
Got
it. So now we have this thing. Now actually, if you look at this looks a lot like I summed up the forces, but with times their lengths. Now that's literally what torque is. That's the same thing, but you can think of that. There's another rule for this. This is before they trust you to learn about torques correctly. Before they do that in like high school, sometimes they'll tell you like, there's a thing called the lever principle. And the lever principle says that if you have like a thing on a lever, that the things that should balance are the force here times the distance, F dot D, and if this is, if this is D1, D2, and this is this has a force F1 and a force F2, then F2, D2 has to be equal to F1, D2, and they say, I call this D1 like the leverage of this force. And if you double it, you double the leverage. Okay, that's fine, but there's a perfectly good way of talking about that, which is literally this is torques. This is a torque at this point. So anyway, so this is another intuition that I think is very common, that, well, of course, if you apply something farther away, it's somehow better, and it's because of this magical property called leverage or whatever. It is, that's fine. It's just not magical, and it's not called leverage, it's called torque. And you've doubled your torque because of this. So, and often they become very simple like this. So the torque equation looks very weird and complicated. It has a cross product in it, and it comes in a weird direction, but it's literally just leverage. That's literally what torque is. Anyway, and so now we can just solve for, what do we care about? Oh, t, right? Everything else is known. We can just solve for t, and we get something. Let's just do that to see the limits, because that's kind of cool. So we get t is, and we move everything over, we get m g d over 2 plus little m g d all over d sine theta. And now the d cancels everywhere. Okay, and now we get t is m over 2 plus little m all times g over sine theta. That's the tension of the wire, of the cable. So now we're actually making a statement about the rope. I used 3 different words for it, but that's, you know what I'm talking about. So, okay. So let's take some limits. What if sine theta went to 1? That means that the angle went to 90 degrees. So somehow you attach it up here. well, okay, you get, whatever, some number, m over 2 plus little m. Okay. Actually, that kind of makes sense because that means you have to lift this one completely and you only have to lift half of this one because it's sort of at the center. Because, in other words, this lifts the other half. Like if two people lift something with something halfway between, you only have to lift half. So that means so that's kind of what this is saying. You get half of the force from the center of mass and you get the full force from the thing that's on your side. So anyway, now what if you try to attach it like here? You try to attach the tension here, right? That seems really dangerous because it seems like then, and actually we can think about this in components, if we have a thing with a bunch of force down and we have another thing where we're trying to attach the tension, this is a very low angle. Well, this tension actually has two components, right? It has a vertical component and a horizontal component. And we need the vertical component, which is small because it's at a low angle, to be equal to this, right? Otherwise the forces aren't going to cancel. But if we need this to be huge, if it's at a low angle, this must be even bigger, and therefore the full tension must be huge. And if we take theta to be very small, we can see that we do get a huge, not an infinite, right? So as the angle goes very low, and you again try to imagine this, trying to hold something up by like pulling along its length, like trying to pull a cord here that holds us up, you'd need to pull really, really hard, even if it's not that heavy, because you have basically no leverage. That's the sine theta from the torque equation, right? So does that make sense? So once we solve this is totally, we could just solve this and we could get this, and this is true, okay? This is true, meaning this is what t actually equals, and now we could go back to this equation here and we could fill in t, right? And we get something. And we could actually solve for the force. Now, in this case, I was just talking about the vertical components. We could solve for the force of friction, meaning the vertical component of this F that they drew in the picture. Because that's the vertical. Now we could also talk about the horizontal forces. What are the horizontal forces? Well, the only horizontal force that, besides this point, is the component of the tension force, this component of the tension force, and therefore it must be equal to the component of the normal force. And once we have those two, we could take the sum and get that F that they were talking about. We don't even have to call them normal and friction. We could just call them components too. So even if you didn't think of breaking this into the actual physical components, you could just call it the X component and the Y component of F. So according to their notation, we would just say the components of F. Once we have the components of F, of course, we have the F itself. So we basically did two steps. Well, the first one, we use torque around this point to ignore these forces. Then we use the sum of the forces, just not rotating at all, just linear forces, and we obtained everything I mentioned, I guess. That's kind of everything. We could have, instead of doing the sum of the forces to get this, we could have also talked about the torque around this point. Then T and this wouldn't matter, but this would have to equal this, right? And if we even included this, we could call it F sine theta, and then we could actually solve for F in one step. But anyway. So those would be equivalent, but it doesn't really matter. There's no right. Neither of them are right because they're all true. They're actually the same information, sort of. You can kind of see these equations don't look very similar. Like we still have the same types of terms here and here, but the fact that we have like a 1/2 here, not a 1/2 here, is very, very important. That will affect our answers completely. So how was all that?
Follow most of it.
Okay. Okay. Yeah, it's this is one of the harder things,
Yeah.
as I said. All right, I'm gonna stop this.